All right, we're almost ready to get to permutations, but let me first show you factorials on the Google calculator. It's really straightforward. First, I'm going to find the Google calculator. I was just typing 3 plus 4, 3 times 4. Okay, that actually didn't work, so I'm going to do 3 times 4. There we go. Ah, there it is. There's the Google calculator. And then here we go in here, and for example, we have 1 factorial. There we go. 2 factorial, which is 2. 3 factorial, that should be 6, right? 4 factorial. So 1 times 2 times 2 times 3 times 4, and then 5 factorial, 1 times 2 times 3 times 4 times 5, and so on, 120 here. All right, let's look at the permutations. And for permutations, when you take them, you have a certain number of objects, like 12, and you take 3 at a time, and the order matters. So the permutation then becomes 12p3, just like it says here. And here's the original formula. This one looks more complicated than really what it is. So the n here would be a 12 factorial, and then this here would be a 12 minus 3 factorial, which they show here. So divide by 9 factorial. Now on the Google calculator, that can be easily done as well. So I'm going to do 12 factorial, which is a pretty big number. There you go. And I divide by the, well, 12 minus 3 is 9, so I'm going to divide by 9 factorial, which makes the number quite a bit smaller, 1,320. And if you look at this one here, I believe I got it here, there we go, there it is, 1,320. I'm going to show you a few permutation calculators for some of these problems here. So 5 objects taken out of 8, 2 out of 32, and you see here the results, and keep them in mind, respectively. You have access to the textbook anyway. So I'm going to go over here, and here's one. This is Symbol Lab, and let's see, what did I have? Oh, I did actually have 8p5, so 8p5, and it doesn't matter if I use capital P or lowercase p, and there it is, and you can see that one in the book. This one here, let's see, there was a 32 and 2, and then click this one here. And this one here calculates permutations and combinations, which I'll talk about later. So this is a pretty cool calculator because it shows us 2. Let me give you another example here. So 14 and 4. So I'm going to pick 4 out of 14. So I'm going to calculate that. Should be a relatively large number, 24,000 permutations. So you're starting with 14 objects. You pick 4 at random out there. How many possible permutations could you have? And the order matters. And this one here comes out to 24,000. Now, if the order doesn't matter, so as you have the permutation of the 4 objects that you picked out, which is by itself actually 4 factorial would be 24, notice that a combination where the order then doesn't matter is 24 times smaller. I think you can see that here. 24,000 divided by 24 is 1,000. So for the combination, the order doesn't matter. For the permutation, it does matter. So the combination is a whole lot smaller than the other number. Earlier, I think when I talked about the Smurfs, I put a couple of, hopefully, bubbles in my recording that says, oh, I accidentally used the word combination. I should have used the permutation. Turns out, actually, the textbook was doing something similar at some point. I found it. There it is. There it is. So here, there are 15 entrants, and prizes are given to the top 3 finishers. How many different combinations? This is what the book is saying. I actually will put this one in parentheses. Your better permutations of top 3 finishers could there be? So 3 out of 15, and the order matters. So when I go back here, 15, 3, and there we go, 2,730 permutations. Here's another calculator, 15, 3 out of 15. There's the same number, of course, and I think there was a problem in here in the book, 4 out of 15, and again, the order matters, so 32,760. All right, this is my second take actually for this one. Earlier I was muted. So here we go. I'm not sure if I talked about this one in this particular recording. Gosh, that's so many of them, so many, no, not that many takes, but still, 2 or 3 is more than 1, and it takes quite a while to do all these kinds of edits. So here I have, for this big permutation, I have 52 playing cards, and I take all 52 out of them, and basically I'm actually back to just factorial, because I'm taking all 52. So 52 factorial is that pretty big number, and how many ways can you shuffle the cards, and then you come up with these 8 times 10 to the 67 permutations, so 8 with 67 digits behind it, and it's such a huge number. So every time you shuffle the cards, the way they're arranged is a completely new way. You know, like no one ever has shuffled the cards like that, because the permutations are so many, there's so many of them, that repeating any one of them is just immensely improbable. All right, so, oh, this one I just did here, 15, 4 out of 15, right, the Monopoly one. So let's see, I'm going to go back to the swimming one here, because I want to show you something with these here. So here I have 8 swimmers, and it matters in which place they come in to medal for the gold, silver, and bronze. And this one here is pretty cool. All right, we put in the 8 and the 3, so I'm just going to change it to something else, like 15 and 4 again, to show you. There we go. And now I'm going to change it back to 8 swimmers and 3 finishers, 336 permutations. These names that I wrote down here, these are the last 8 world champions over the last 20 years in the 100-meter track and field, not swimming, track and field. So I think this is, Shelley and Fraser and Sha'Carri Richardson is her name, and Tori Bowie, excuse me, Veronica Campbell. Some of these are U.S. American, some of them are Jamaican, and this one here is Zana Pintusevich, who is from the Ukraine. So this one is pretty cool. It tells us there are 336 permutations, if they had run against each other, how they could have placed in the top 3. And it lists all of them. So there it is. So here we go. I could say, okay, out of these 8, I pick 3, and this is how they could have had the gold, silver, and bronze. And there is the second combination, and here's the third permutation. And then I go down here, and this is perhaps the 50th permutation, and then this one here is the 100th permutation, and then all the way down here is the 335th and the 336th permutation. That's how they could play. So this one is pretty cool. If you want to test this one here, I could put the Smurfs names in there and so on, and play around with it, of course. All right, before I stop this one here, let me do one more. Apparently 8 and 3 is very popular, so I'm going to do 8 and 3, and so I'm going to continue on here with combinations very soon. It's actually late in my office, and I'm going to give myself a break, so I will record this later. Notice there are 336 permutations when the order matters, and 56 combinations when the order doesn't matter. Notice the computation is slightly different. So let me show you these here too on the Google calculator. So this one is basically 8 divided by 5 factorial. I think you can see that, 8 minus 3, right? And here's 8 factorial divided by 5 factorial and 3 factorial, because the order doesn't matter. So the first calculation would be 8 factorial divided, not divided, start over again. 8 factorial, yes, was correct, divided by 8 minus 3, which is 5 factorial. There we go. That would be a permutation of 336, but in here the order matters. And then I divide by 3 factorial when the order doesn't matter, and now we are combinations, so that they are related again. Permutations are much larger than combinations. All right, so here we're back to these 8 competitor Smurfs for this swimming or track and field example, and on the permutation. So when you do the factorial or the permutations, 3 out of 8, you can choose 1 out of the 8. So you have 8 possibilities, then 1 of the remaining 7, so you have 7 possibilities, and then 6, 1 of the remaining 6, so you have 6 possibilities, so 8 times 7 times 6, gold, silver, bronze. Those are the, was it 336 possibilities, permutations that we've mentioned several times. And when you do that with, this was here, that was actually the permutation. So the other way of doing it would be then 8 factorial divided by 3 factorial. Okay, so what's the combination then? Well, the combination is that it doesn't matter if they place gold, silver, and bronze, where between just these 3 here, of course, we have these 6 possibilities, right? There we go. And I think I got all 6 possibilities, even though my hands were in the way. Maybe I should have done that from the other side. So if the order actually doesn't matter, then the possibilities are 3 factorial, 6 times smaller. So 336 divided by 6 would be 56 combinations that we have now. Now, when would that matter? Well, it mattered, for example, if I have like 8 players to choose from, and I can only field 3 of them, but it doesn't matter in which order they are, as long as they're just on the field doing something. You know, they're on my team. It doesn't really matter the order. So that would be one example, and that's actually one of many examples. Another one is actually, you will see that later in the videos, that for the Olympic Games, it matters who's going to place gold, silver, and bronze. So there's the permutations. But then for the US trials, actually, when they want to get to the Olympics, it doesn't matter how you place first, second, or third. As long as you're in the top 3, you will qualify for the Olympics. So for those US trials, it actually doesn't matter in which order these are, but you have to be in the top 3, and you only come up with 56 possible combinations. So that's the difference between the permutation and the combination.